Hi, thank you all so much for joining. My name is Seth Weisman. I am a solutions architect at Verica and committer on Apache Flink. And I'm really excited to be giving this hands-on demonstration of building stateful serverless applications using Apache Flink stateful functions. So because this is a hands-on talk, the agenda is very brief. We are going to quickly take a look at what stateful functions is in case you're unfamiliar, but then very quickly get into some application development. So what is stateful functions? Well, it's an API that simplifies the building of distributed stateful applications. So if you've used Flink in the past, right, you know the table API. Well, that is something that simplifies the building of continuous aggregations, real-time reporting. Stateful functions is a new API that exposes Flink runtime for the other end of the streaming spectrum. Use cases where things like microservices or function as a service platforms are underserving the community. And so what we've done is taken the benefits of stateful stream processing, the processing of large data sets with low latency and bounded resource constraints, and bundled that with a runtime that is built for serverless architectures and supports modeling stateful entities with location transparency, concurrency, scaling, and resiliency. When building a stateful function application, users are able to define several services, or what we call functions, that are basically tiny bits of code or logic that represent entities within an application. So we could, for example, define a function type representing a user with a single instance of that user for every single user within our application. The function instances are invocable through messages and don't consume resources while inactive, or simply when they're not being invoked. So this means that our runtime is able to support a theoretically infinite number of function instances within a fixed finite set of resources. And this is a polyglot API. So while we are leveraging the trusted and battle-proven Apache Flink runtime, which is written in Java and deployed on the JVM, that is not a requirement for our user code. There's a fairly simple protocol that you can implement in any language to write your user code. So anything that supports HTTP, gRPC, Unix sockets, basically any language in practice can be used as user code. Of course, you don't want to be doing that every single time, and so we do offer a number of predefined SDKs out of the box. Next thing that's really important is this idea of dynamic messaging and consistent state. Unlike Flink's data stream or table APIs, we do not predefine data flow DAGs. Instead, any function can message any other in arbitrary, cyclic, even round-robin ways. All you need to know is the logical address of that function, what we call its function type and ID. There's no service discovery required. You don't have to look up where some code is running. It is fire and forget. Yet, the runtime will ensure that we have consistent state in messaging. So we are still retaining the exactly once semantics you expect from Apache Flink. And this ensures that each function can maintain local state, and the runtime will guarantee that messaging and state updates are integrated so that users can have out-of-the-box efficient consistency across the global application. Yet, again, sticking with Flink here, this whole thing is no database required. And this is really important for leveraging these modern deployment architectures. So we can run our code on something like Kubernetes, where we have task managers as various pods, yet we don't have to deal with things like persistent volumes or stateful sets. All we need is simple blob storage, and we have our persistence. And then the final notable thing here is that we're really leaning into this idea of serverless architectures. We want your user code to be able to leverage modern serverless platforms like AWS Lambda or Kubernetes deployments, maybe choose something like Knative. And this gives you the operational management benefits of these platforms like rapid scalability, scale to zero, and zero downtime upgrades. This is all possible due to some runtime choices that you can see in this diagram. A stateful functions application is composed of a Flink cluster for messaging, routing, and state management, while allowing your actual functions containing the application logic to be deployed on a separate compute tier. This gives us a runtime where compute and state are logically co-located for consistency, yet at the same time physically separated. The state tier, being the Flink state fund cluster in this diagram, is deployed separately from compute, which means that our compute is in practice stateless. We can have idempotent retries. We can have things fail and come back up, and that's okay because Flink is ensuring our consistency. All state accesses and updates are integrated as part of our function invocation request and response. But that's enough background. Let's dive into some technical details and see what it means to really build something using this API. So it touched on just a second ago, there are two different types of SDKs currently supported. We can either have embedded functions that run directly inside a task manager, same way data stream table API work today, but that's not very interesting. I want to focus on remote functions. And these are essentially the building block of our code, and they can be implemented in any language that defines our protocol. Out of the box, we're shipping Python, Golang, Rust. There's even a Haskell one that's recently popped up. And they communicate with the Flink cluster via a well-defined remote HTTP request reply protocol. So in your function, right, the place where you're writing your user code, we're able to send messages to other functions, send messages to an egress, right, output it from our application, and persist local state. They also have some other capabilities like sending asynchronous messages, sending messages with delays, and so forth. But these are kind of the core primitives that the runtime is going to provide us. So we are writing remote functions, right? Our user code could be in any language. Functions in any two languages can communicate with each other arbitrarily, right? A Haskell function could message a Python function or vice versa. And it's all being routed through the Flink runtime that is deployed on the JVM. So we need a common framework to allow these different components to communicate with each other and a common serialization format. And for that, we have standardized on protocol buffers, which is a serialization standard that came out of Google and has a lot of very nice properties. It's cross-language, and it offers schema migration, which is very important for stateful applications. And in particular, because different components don't know what to expect from each other, all messages sent between functions and all records stored in state must uniformly be protobuf any, which is effectively the super type of all protobuf records. This is really convenient because it contains the serialized bytes along with a URL describing that type. And so receiving functions are able to unpack, quote unquote, that any message into a concrete type using their language-specific protobuf library. So to illustrate this, we have a Python function. And on the right, we have some other function that might be written in Golang. All messages sent to remote functions must be protobuf any. And here that sent message says, I am a greet request, right? This is my type. And here are the serialized bytes. When the Python function receives this message, it is able to unpack it into its Python-specific implementation of a greet request, and then work against that concrete type. So that's what your user code is going to see. If we want to message some other function, again, we are going to pre-wrap it into protobuf any, and then send that across the wire. At the other end, we're going to see, hey, we got a greet request. Here are the bytes. Let me deserialize this into my language-specific library. Same goes for state types. As I mentioned, they must be protobuf any. This means that state written in arbitrary languages can be uniformly maintained by the Flink runtime. And our state backends only ever see serialized forms as wrapped any. So we don't need to worry about types or languages. It's just bytes in and bytes out. That said, I know this sounds a little boilerplatey. In practice, it isn't, right? The low-level protocol might work with protobuf any. However, all the SDKs offer higher-level abstractions and utility methods. That means in practice, your user code typically only develops against specific protobuf types, such as we see here. So as with any good introduction to a new piece of software, we're going to start with Hello World. But I want to do this in a way that really shows off the key characteristics of a stateful function application. And so we want to do it statefully. We are going to generate greetings for different users, but we're going to personalize them based on the number of times that specific user has been seen so far. That means we have to maintain state. I have to keep track of how many times I've seen a particular user up until this point. And so a stateful function in Python is going to be any function that takes in two parameters, a context and a message. The context is what gives us access to our capabilities. We can read and write state, we can message other functions, we can do all that good stuff. And then the message is, of course, the message that was sent to us. Each function instance is associated with a function type and ID. So you can imagine that for every user within our application, there always exists an instance of this greet function class, quote unquote, that handles the request for that specific user. Each function instance has this unique logical address that is made up of both the type and a unique ID for that user in this case. So think function type is kind of like class in object-oriented terms. And address is a particular instance. It's made up of the type and a particular ID. Might be our UID for our different users. One thing we can see out of the box is that using Python 3 type hints, we are able to automatically unpack our input messages into specific protobuf types. So, we're not dealing with any of that protobuf boilerplate in practice. We are able to use our context to also do things. So we are sending messages to another function. In this case, we have a function that sends emails with our greeting to our user. And we are going to automatically pack and send that any record before send. Automatically pack our record into any. When we want to invoke another function, same way that this greet function was invoked, we are going to message its address, which again contains the function type, demo/email sender in this case, and the ID. Right? These are always logical types. I don't know what language our email sender was implemented in, and frankly, I don't care. It doesn't matter. We are simply firing and forgetting this message. The runtime will take care of the rest. And so now let's get into what I think is the most powerful feature here, and that is durable state. So this is a snippet of what create personalized greeting might look like. And in this code, all we're doing is keeping track in durable state of how many times we've seen a user and creating a special greeting based on that text. So state is accessed and updated using our invocation context. And we have pack and unpack to work against specific protobuf types again. So once more, no boilerplate here. We're really working against concrete types. Other than that, there's really nothing stateful specific here. Instead of using a local variable, I'm using the context to keep track of my state. But otherwise, this is plain old Python code. We're going to check our account, we're going to update it, we're going to generate some text, and we're good to go. And so now that we've implemented our function, the last step to do is expose this function to the runtime so it can actually be invoked. And the Python SDK, along with the others, ship with constructs to do that conveniently with any HTTP framework you prefer. So first thing we need to do is bind multiple functions, or if we have multiple functions, to what I'm going to call our function registry. This is what keeps track of logical function type to physical Python function. And we are binding both our greeter and our email sender in this case. The SDK also ships with a request reply handler, which is going to dispatch requests via HTTP to bound functions. And so this is the thing that's implementing that low-level protocol. This is going to handle encoding all of our side effects as well, and returning the results and our updated states to the Flink runtime. And this handler can be exposed with our favorite HTTP web framework. I'm using Flask in this case, but you can use whatever you like. So this is the Python code that we just saw for our greeter function. And I want to go ahead and package and deploy this application. The first, and I think most important thing to note, is that there's nothing particularly special about what I'm about to do. I have my requirements file that contains the Stateful SDK, along with Flask to actually serve our REST endpoint. And I'm going to package this inside a Docker container, but there's nothing Flink specific here. This is a standard Python application. we don't care that there is a Flink cluster running somewhere else, at least in terms of how we package our user code. It is just Python. But that does lead to the obvious question of, what do we do on the Flink side, right? How does the Flink cluster know about our code? And for that, we write a simple module YAML file that defines all of the actual functions that exist and are invocable via the runtime. So as you can see, I am defining my function. I only have a single one in this example that contains the type of function. So we're saying that there is an example greeter. That is the function type available. When someone wants to message this function type, I know how to get there. And what do we do? Well, it is exposed via an HTTP endpoint. And here's the specific endpoints that we can use. So in this example, I'm using Docker Compose to run this whole thing. And so my Python worker is going to be made available via this endpoint. The other thing we have to do for HTTP remote functions is eagerly declare all of their states. We don't need to know the type. We don't need any of the protobuf information. We simply need to list out the states that are need to be made available. So that gets us our user code, and the actual Flink cluster is going to know how to work with this module. But we still need to connect to external systems. I need to read data off of Kafka that is going to be my greet requests, and I need to write results to Kafka that are my greet results. So for that, we have an ingress and an egress. An ingress defines an entry point into the system. And so in this case, we are using a Kafka ingress that is named example names. And then we have some Kafka-specific configurations. So I know the address of my brokers, my consumer group, and the actual topic I want to consume from, along with the type that we expect to read out. So we are reading out greet requests. The one maybe interesting point here is our targets list. So for each record we read off this topic, we need to know what function to send it to. And our targets is a list of function types that each message should be sent. They should be routed to those functions. So in this example, we are reading a greet request and we are routing it to our greeter function type. Of course, before I said we invoke functions via an address that is a function type and ID. In this case, our user UID. Well, the ID is implicitly pulled from the key header of our Kafka topic. So these requests are being written with that information encoded in the header, and so we can just get it. If we were using something like Kinesis, we could also pull that key information. And for our results, we're sending our data again to a different Kafka topic, and that is our egress, so example greets. Once more contains basic Kafka configuration, so we know where our brokers are. We're doing exactly once delivery because we want to only have the most correct results. And in our user code, when we send a message to example greets, well, the runtime knows, hey, that's actually a Kafka topic. I will write out that data and we are good to go. We now take this module file and add it to the Flink Stateful runtime. So the community makes these images available. It contains the full Flink cluster, all the Stateful specific runtime code, and all you need to do is add your module file. On startup, the runtime will discover this file and configure itself for your specific application. There's no Java code here. There's no user code inside the Flink runtime. All right, so now that we have written our code, it is time to execute this application. I'm running everything locally using a simple Docker Compose, and you can see we have all our different components up and running. There is our Flink cluster made up of a job manager and task manager. There is our Python user code function, and then I also have a small Kafka cluster along with an event generator that is generating greet requests. Down here, I am printing the result topic from Kafka, and we can see all these different greetings that are personalized to each of our users, Jerry, Newman, Frank, and Kramer. And so on the right, we have our Flink cluster. And what we see when we look over here is that this is a very simple Flink application. It's reading data in, there is a main operator, and then data is going out. One thing that is unique about stateful function applications compared to other Flink jobs is that our data flow DAG, our underlying representation, is static. No matter how many functions we have, no matter how many languages we are implemented in, our physical job graph is going to be very simple, which makes our operations much easier because things don't change as our user code does. But we'll see, records are being processed. I can go in, we're taking checkpoints so we know things are happening persistently. We can also tell that because, of course, I'm only writing out with exactly one semantics. But to prove that, let's do something. I'm going to go ahead and restart a task manager. Docker compose restart worker. And if you've worked with Flink before, I suspect you know where this is going. The task manager is going to restart, and our job is going to restore from the latest checkpoint. It's as if we had some massive hardware failure. But because we are running with exactly once, because we have Flink checkpointing under the hood, we know we are going to get consistent results. And when this job fully restarts, we will see that our greetings continue to pour out, and there are no duplicates, there are no lost records. We are going to start from exactly where we left off. And that is precisely what happened, right? Records continue to flow out, the job is back up and running, and here we are continuing on as if nothing had ever happened. So this is great. We have seen how to build a stateful function application with user code running remotely from the Flink cluster. Our code is stateful, it's fault tolerant. We know how to configure our modules. We know how to interface with external systems like Kafka. But you're not building Hello World apps. You are supporting real businesses. So let's take what we've learned here and expand upon it in a real world use case, building a ride-sharing application. So this diagram shows the basic application we're about to build. We are implementing the core functionality of a ride-sharing service, the component that actually connects passengers with drivers. We need to know the status of any given passenger or driver within our system, whether or not they're taking part in a ride, requesting a ride, or free to pick up a new passenger. We have a geo-index that tells us where people are physically on the map, so that we can connect drivers with passengers based on physical proximity. And our ride function that ties it all together. It finds passengers who need drivers and gets everyone on their way. So I've decided to go ahead and implement this ride-sharing application using the Golang SDK. All the concepts we learned while writing our greeter with Python are going to translate over here. The stateful function protocol that these SDKs implement offers the same functionality regardless of language. So we can still pass messages around, we have access to state. Some things may look slightly different as we try and make each SDK idiomatic to that language, but the basics all translate. This time, I want to tackle this code in the reverse direction of what we saw before. So I'm going to show you how everything gets tied together, and then we'll look at some interesting parts of these different functions. So inside of main, we're creating a stateful function registry, just like we did before, that maps function types defined above to our actual functions. And a function, stateful function, is anything that implements the stateful function interface defined in the Golang SDK. So in this case, we have 1, 2, 3, 4 functions. Our cell, driver, passenger, and ride that we just discussed, along with their implementations. And this registry implements the standard Golang HTTP handler interface, and so it can be easily exposed as an HTTP endpoint. In our module.yaml, we are going to be able to message these functions and define them just as we saw before. There's nothing Golang specific, there's nothing that I changed about the way that I set up this file for this application versus the other. It's all just remote functions. So one thing I would like to note is that all 4 of these functions have been implemented in Go, and they have been implemented within the same executable, but there's no requirement that we do so. Each of these could have been written as different applications that were deployed separately. They could even be written as in different languages. The passenger function, for instance, could have been written as a Python function deployed on AWS Lambda. Because everything is using protobuf as messages, different functions, they can all seamlessly communicate with each other. The fact that it's one executable is really just for simplicity of this talk. So above is where we defined our function type. Remember, this is the logical name for a type of function. And I have all four defined. In Python, this was a string with a slash between the namespace and type. Here, it's a struct because that felt a little more Golang idiomatic, but it's all the same thing. We also defined the names of our two egresses, which are how we send messages to our physical passengers and drivers respectively and respectfully. And we're able to now tie this all together. So let's see what some of our functions do and how they communicate with each other. Starting with how a passenger requests a ride. So this is my passenger function, and it is implementing the stateful function interface, which is any function that has these three parameters and returns a potentially nillable error. Unlike the Python SDK, it takes in three parameters, and that is because in Golang, context is a well-defined type, and we want it to remain idiomatic. So we pass the Golang specific context here, along with the stateful function runtime that offers the state management and messaging functionality we saw in the Python context. Message that is passed is still protobuf any, so we're free to work with it as we please. When a passenger wants to request a ride, we're going to get this inbound passenger message. And so if we're able to deserialize this, if that was the type passed, we're going to go into this function. And to kick off the process, what we need to do is message the ride function that a passenger would like to join a ride. So we're going to get our passenger ID from our context. We're going to generate a random ride ID as a UID. And then we're going to message our ride function for that specific ride, telling it the passenger's information, right? Who is this and where are they? Inside the ride function, we can now follow this message. So this is also a stateful function. And when its message is the passenger joins ride that we just sent, well, it's going to do a few things. First of all, we have to remember what passenger wants to join this ride, and so we'll set it into state. And then we'll message the geocell that this passenger is currently located in, asking for an available driver. We'll follow this one before moving on, but inside of our geo function, excuse me, this is the one I want. Inside of our geo function, when we get our get driver message, it is going to check its state, which contains a list of all the drivers in this cell. And it will either respond back with an available driver or say, hey, sorry, there's no one available. This code is fairly complex. It follows through a number of different paths. We're not going to walk through all of it right now, but I encourage you to take a look. It is all available online. But so we have written all of this code in my module.yaml. We have defined our runtime, so we've said what functions exist. We know they're invocable via HTTP. We've also defined our ingresses and egresses, so we have Kafka topics to read in information about drivers and passengers, along with egresses to write our data out. Remember, these are the same IDs we saw defined in code. And so now we are ready to deploy this application. All right, so it's now time to go and deploy our application. Unlike before, I'm not going to run this locally, but we're going to do a full-blown Kubernetes deployment. I've already installed some Kafka brokers for our topics. There's also MinIO for checkpointing and a data simulator that is simulating tens of thousands of passengers and drivers that want to connect with each other for rides. So if we take a look at the pods inside this cluster, we can see that there is the Stateful cluster, the Flink cluster, that is based on that Docker image containing our module.yaml file. And we also have our user code, our Go functions. These are running and deployed on our cluster and being messaged to and from by the Flink application. If we go into the Flink UI, the first thing that you should notice is that the topology has not changed. We're running 4 functions for our ride-sharing application instead of 1 for our greeter, but it's still the same physical job graph. This makes our deployment very stable because things that affect Flink network usage and bandwidth are not being affected by our user code. We can also see that we've processed a good amount of data over the past day or so. We're only running Parallelism 10, but we've processed nearly 0.5 terabytes of records, and I think that's pretty good, especially since we haven't spent any amount of time really optimizing, any of our user code application. We can go into our checkpoints and see that those are going through nicely. So we've taken quite a few checkpoints. No need to restore. Everything is running stably. And overall, I'm very happy with this. But, I maybe went in and took a look and saw some metrics, saw the Kafka lag, for example, and discovered that we were falling behind, right? We're not able to keep up with the flow of data. Our ride-sharing app is just too popular. So what should we do? Well, because we have separated compute from state, we can very easily rescale our compute tier without any downtime. Where there's a data stream application, I would have to take a save point, stop the job, add more task managers, restart the job from that save point. That takes time. Taking advantage of Kubernetes and our stateless compute tier, we can simply rescale. So I could go into my deployments and rescale from 10 to 20, for instance. But I don't want to do that because maybe we're in a high traffic time and it's going to die down. I don't need 20 pods forever. So instead, we can take advantage of auto-scaling. And so I'm going to apply this auto-scaling policy that will scale our compute between 1 and 20, depending on CPU utilization. And we're going to target 50% CPU. So I can go ahead and apply this policy. And in just a moment, it will take effect. So let's go ahead and describe our horizontal pod autoscaler. And I clicked it a little too soon, but you can see that it is going to look at CPU utilization and check if it's over 50%, and then rescale up or down depending on where we land. So I suspect if I take another look, yes, it determined that, hey, we were way under provisioned. We were at 500% CPU. That is way above 50%. And so we are going to scale up to 20 pods. And if I now take a look at the pods available, you can see there are a whole bunch that were just created just a few seconds ago. And because the Stateful cluster, the Flink cluster, is messaging our compute via a load balancer provided by Kubernetes, we are immediately able to take advantage of this extra compute. Using these same tools, if we needed to deploy a new version of our code, a bug fix, we could also do so without any downtime. We're really just treating Flink as our database. So thank you all so much for joining on this talk. It's been a lot of fun to give, and I hope you enjoy the rest of this virtual Flink Forward. Thank you.